Degree of integration. Fields and holders of duties within any organization are connected by informational relations, meaning that the fulfillment of the said duties largely depends on the degree of data integration. Once data is viewed as a factor in production, it must be planned, governed, monitored, and controlled. This makes it necessary to see data management as a task. This statement suggests that the efficiency and effectiveness of job duties within an organization depend on the extent to which information is integrated and easily accessible. For example, if different departments within an organization are using disparate systems for storing and accessing data, it can lead to inefficiencies and redundancies, as one department may not have access to the latest data from another. This can make it difficult to make informed decisions and can lead to miscommunication and errors. On the other hand, if all departments have access to a unified data source, it can improve collaboration, streamline processes, and facilitate better decision-making. For the executive level, inducing a major change within the company. The computer-based information system in Figure 1.1 is connected to a communication network, such as the World Wide Web, in order to allow for online interaction and global information exchange in addition to company-specific analyses. Any information system of a certain size uses database systems to avoid the necessity to redevelop database management, querying, and analysis every time it is used. The statement is highlighting the importance of using database systems within computer-based information systems to avoid the inefficiencies and redundancies that would arise if databases were redeveloped from scratch for every use. Additionally, the statement is highlighting the use of database systems in larger information systems. These databases help to prevent redundancy of work because they pre-store certain functions, like querying, database management, analysis, that can be used time and time again, instead of having to redevelop them every time they are needed. Pre-storing certain functions means having a set of standardized functions that can be reused across different use cases within the database. These functions might include operations like querying, sorting, and manipulating data. A database that pre-stores functions is essentially a static database, meaning the functions and data within it are relatively stable and do not change frequently. Dynamic databases, on the other hand, are more adaptable and responsive to changes in data. They are designed to handle data that is constantly changing, such as in a large social media platform where user-generated content is constantly updated. In a dynamic database, the structure and data stored within it can adapt and change to accommodate new information as it is added. This allows for real-time data updates and allows data to be queried and analyzed as it changes, rather than being fixed at a single point in time. There are several approaches to creating a dynamic database, depending on the specific requirements. Some common techniques include using a schemaless or semi-structured data model, such as NoSQL databases, which allow for more flexible data storage structures. Implementing a change data capture system, which tracks and records changes to data over time. Using replication techniques to automatically propagate changes across a network of databases. Using triggers and stored procedures to automatically update the database when certain conditions are met. Triggers and stored procedures are ways to add custom code to a database system that is automatically executed when certain events occur. Triggers are special types of functions that are automatically executed in response to an insert, update, or delete statement on a specific table in the database. They can be used to enforce data integrity by performing additional checks or actions on the data being modified. Stored procedures are essentially precompiled SQL code that is stored in the database and can be executed on demand. They can be useful for encapsulating complex database operations and preventing code duplication within an application. Triggers and stored procedures are similar in concept to an ASDL file in Python or a superclass in Python. ASDL files contain definitions for actions and events that can be executed on demand, while triggers and stored procedures store precompiled code that can be executed automatically when certain conditions are met. Similarly, Python superclasses contain the blueprint for a class and define common behaviors and properties that can be shared among different subclasses, just like triggers and stored procedures define the behavior and actions to be executed under specific conditions. Precompiled means that the code within trigger or a stored procedure is compiled, or translated, from source code into executable machine code before it's stored in the database. This means that when the trigger or stored procedure is later executed, the database engine doesn't have to compile the code on the fly, which can improve performance by reducing the overhead of parsing and compiling the code every time it's executed. High-level programming languages like Python and C, there is usually a distinction between compilation and runtime. In those cases, the source code is first compiled into low-level machine code and then executed at runtime. However, when it comes to triggers and stored procedures in a database engine, the term compilation is often used in a different sense. Instead of compiling the source code into machine code, the database engine compiles the SQL code into an internal representation that can be directly executed by the engine. This internal representation is typically a form of bytecode that is specific to the database system. In other words, while we are working at a higher level of abstraction in the sense that we are using SQL, a high-level query language, the internal workings of the database engine involve translating our SQL code into a form that the engine can execute efficiently. This form is often referred to as compiled, but it's not the same kind of compilation as in high-level programming languages like Python and C. Additionally, the process of precompiling SQL code in a trigger or stored procedure is independent of partitioning in the database. Partitioning is a technique used to divide a large table into smaller, more manageable parts, called partitions, to improve performance and scalability. It involves separating data into different groups or ranges, such as by date or hash, and storing the partitions on different file groups or storage devices. In contrast, precompilation of SQL code is an internal optimization technique used by the database engine to improve the performance of triggers and stored procedures. It is unrelated to the physical layout or location of the data within the database. Precompiling SQL code in a trigger or stored procedure is a process that happens at the database engine level. It is independent of the way the data is physically stored or partitioned in the database. The precompilation process involves taking the SQL code that is used in triggers or stored procedures and converting it into an internal representation that can be more efficiently executed by the database engine. This internal representation is stored in the database and is executed when the trigger or stored procedure is called. So, the physical storage and partitioning of the underlying data does not affect the precompilation of the SQL code. Sharding and partitioning are two similar techniques used to improve database scalability and performance, but they differ in how they are implemented and what they aim to achieve. Partitioning involves dividing a single table into smaller partitions based on a certain criterion, such as a range of values or a hash function, and storing them on different storage devices. It is often used to improve the performance of queries that access a large table by breaking it down into smaller chunks that can be accessed in parallel. Sharding, on the other hand, involves splitting a single table into multiple shards, each physically located on a different server or instance. The key difference between partitioning and sharding is in the physical layout of the data. When data is partitioned, it is divided into separate physical chunks within the same database instance. Therefore, queries must be executed on the correct partition based on the partition key. Sharding, on the other hand, involves splitting data across multiple physical servers or database instances. This can improve scalability and performance by allowing queries to be executed in parallel on different nodes, but it also introduces additional complexity in terms of data management and synchronization between the different shards. In a way, sharding can be seen as a form of energy parallelization in the context of database systems. Just like how in the field of physics, parallelization is used to divide a problem into smaller parts that can be solved concurrently, sharding also divides a large database into smaller, more manageable parts that can be stored and processed independently. Sharding can help improve performance and scalability by allowing data to be spread across multiple servers, each handling a portion of the overall data, thus reducing the strain on a single server and allowing the system to work more efficiently as a whole. Partitioning is primarily used for database organization and optimization, while sharding is more focused on database scaling and distributed systems. Partitioning is a way to divide a large database into smaller, more manageable parts to improve query performance and is often used with in-memory database technologies like Apache Ignite. Sharding, on the other hand, involves splitting data across multiple servers or database instances and is used to distribute the load and provide high availability and scalability in large-scale database systems. Relational databases are built on a traditional tabular model where data is stored in tables with rows and columns, and relationships between tables are enforced through the use of foreign keys. Non-relational databases, NoSQL, on the other hand, are more flexible and scalable, allowing for the storage and manipulation of data in a variety of formats such as key-value pairs, JSON documents, and graph structures. This non-tabular format offers more flexibility in handling data that does not fit well into the tabular model. Relational databases are typically referred to as SQL databases as they use the SQL, structured query language, for data manipulation and querying. Non-relational databases, on the other hand, are commonly referred to as NoSQL databases, as they are designed to handle large amounts of unstructured data and do not use SQL. NoSQL databases typically use programming languages such as Python, Java, and JavaScript to interact with and manipulate data stored in the database. This is primarily because NoSQL databases are schema-less and can store data in a variety of formats, which can make it difficult to query using SQL. As a result, NoSQL databases often provide APIs and libraries in programming languages that developers can use to programmatically interact with the database. SQL databases, while old, are still widely used for handling structured data and are particularly well-suited for relational data, where there is a need for strict data integrity and ACID, atomicity, consistency, isolation, durability, properties. NoSQL databases, on the other hand, are more modern in their approach to handling unstructured and non-relational data at extremely large scale. There are a few reasons why NoSQL databases might not be used across the board. 1. Legacy systems. Many companies have been using SQL databases for years and have invested heavily in infrastructure, tooling, and development around these systems. Switching to NoSQL can be a complex and time-consuming process. 2. Data integrity. Relational databases are built on a well-defined schema and enforce data integrity through constraints and transaction isolation. If data integrity is 3. Learning curve. NoSQL databases often require a different set of skills and knowledge compared to SQL databases. There may be a significant learning curve for developers and data professionals to learn how to work with NoSQL databases. 4. Performance. Depending on the specific use case, SQL databases can often provide better performance compared to NoSQL databases. This is particularly true when handling transactional and relational data. Data integrity in the context of databases refers to the overall quality and consistency of the data stored within the database. This includes ensuring that the data is accurate, complete, and that any updates or modifications to the data are done in a consistent and controlled manner. In other words, data integrity is the measure of the data being free from errors, corruption, or malicious interference, and that it reflects a true representation of the underlying information or real-world phenomena it models. NoSQL databases often have less overhead and lower fault tolerance compared to relational databases. NoSQL databases are often optimized for horizontal scalability and performance at the expense of data consistency and integrity, while relational databases prioritize data integrity and enforce consistency through atomicity, consistency, isolation, durability, properties. It's common for companies and infrastructures to use a combination of SQL and NoSQL databases. With the increasing demands of modern applications, which need to handle large amounts of data and support distributed systems, many organizations have found that using a combination of both SQL and NoSQL databases can provide the best of both worlds. SQL databases are useful for handling structured data, enforcing data integrity, and providing strong consistency and transactional support. NoSQL databases, on the other hand, are more flexible and performant at handling unstructured data at large scales. By combining both, organizations can build flexible and scalable systems that can handle a wide range